Morning, Virus. Morning. Okay, almost good to go. All right, so right. Well, since they didn't talk about it, I trust you are all aware that there is that CUI capable Gen AI link that was circulated via email. Were you all aware of this? Just because, I mean, you don't need for this class or something in this class that needs to be handled like CUI. It's pretty much open class, open unclass, and I'm not. If you're putting anybody's stuff out, it's probably my stuff, and I'm not that picky. Uh, but as you start thinking about thesis ideas, or if you get something, you get an idea that something in one of your classes could apply to a problem from the fleet, but you need to actually put documents in, as long as they aren't actually secret, you're good. And I think that's going to be really helpful. It's already helped me because I have code for some of my projects that I can't just let out onto the web. It's owned by a contractor. I have it courtesy of the Marine Corps, but we don't want to be, if we're bad citizens, we'll be punished for that, and people won't trust us and give us their code. So I don't want to go there. So yeah, I really like the new thing. It's only got Google Gemini at the moment, but honestly, from what I hear, the buzz on Reddit, which is what I read, is that that's one of the better general purpose models at this particular point in time. Maybe better than ChatGPT, but they're all quite capable. And the other models will be joining them shortly, according to the advertisement on the page. But promises, promises. I'll believe it when the links go live and we actually have access. All right. All right. So, any questions about what we talked about yesterday? So, where are we? So, I gave you a bunch of sketches, right? Just cartoons of balloons and arrows. This is how you could build an agent. Um, so I won't be talking about that again, probably, but I hope it stays at least in the back of your mind, because I think it's a pretty good coverage of the many possibilities, and you'll see those coming up as you go through the curriculum. Any questions on that stuff, or are we good to move ahead? Okay. I mean, I would recommend, again, because the homework isn't absolutely guaranteed to spin you up as much as you necessarily need to be spun up. And it is easy, because I've been there, to just kind of nod through when the professor's talking, they show slides, it kind of makes sense. But I would advise at least flipping through the slides, later on in the week, and try to keep up. Because at certain points you'll look at it a second time and it'll be like, what did he say? That really looks strange. It's not registering with me anymore. And that's maybe time for a question or a little bit of digging. Okay. All right. But that's on you. So I'll do my job here, I hope. Let me find. Now I'm going to say this is the third slide deck. I do revise things as we go. So even like today, like if someone asks a question, I realize, well, that's dumb. He had to ask that. That should have been on the slide. I'll go off and fix that and then update the slide. So be aware that there could be updates. If you want the absolute latest, greatest before the test, maybe go pull it again. Or if you've got a copy that's not matching what I'm saying and it annoys you, I usually do update before class. So usually the slides I'm speaking to are available on Sakai, including this one I'm pulling up right now. So, okay, so now we're going to start for real on some AI that was actually, you could just go off and code. And I don't, so my idea about this is I used to actually do that and have people code, for example, A star being a very important algorithm for us in modeling simulation, but it took more than half of the quarter to get everybody through. I mean, some of us are great programmers. You can go off and do it right the first time. Others not. It's going to take more time. So we're going to be doing it a little differently these days. Mostly you'll be using my code, but you will be writing your own code to kind of stimulate the code that I have and experiment with it, which is one of the modes. So in my mind, one of my reasons why that makes a good lab is because a lot of thesis projects look like that. Some of you are going to write your own thing that you create, and then and then study that thing either with humans or via experimentation on a computer. But others of you will take something that came from a vendor or something that's out in the fleet, You're not going to actually create the code, but you'll be surprised how much work it is just to set it up and write some supporting code around it so you can actually use it the way you want to use it. That's more the model for what will be our lab 1. That's looking ahead of ways. We haven't got to lab 0 yet, but that'll be lab 1. And you will have a chance to a straight up code, I hope, at least one AI algorithm, because I have that in mind, maybe 2 for the last 2 labs. So I won't leave you in the lurch. I'm dying to actually code some AI from, well, more from scratch. At that point, we'll be using standard libraries, so it's still not from scratch, but it won't be my code so much. Okay, right. So the first topic we have here is systematic search. This is the outline. So this is probably the best, most robustly developed and best articulated part of the course because I've been teaching it for 25 years. It hasn't changed all that much. When I started teaching it back in the early 2000s, like no one was using A-star in DoD. I told you, the breadcrumbs thing, that was it if you wanted units to go. They would go like to the point you dropped, but they didn't have any intelligence beyond that. Now this is kind of the lower level, easier AI, and then we'll move on to the harder stuff as soon as we're done with this unit. So we're going to talk about, again, opportunities. It's still early in the curriculum. So in addition to giving you some good CS knowledge along the way, like how we study algorithms and study complexity and stuff like that, where we have some secondary targets we really want to hit as we move along through this discussion. One of the things I want to hit, like starting maybe today, is how do you actually formalize a search problem? Because algorithms and their study it's math, basically. It's math. And problems in the fleet are not math. Also, rarely math. They're anything else, but not that. Okay. So it's up to a smart person who understands what's going on and what is needed to go and bridge that gap and say, yeah, there's this mathematical thing here. Okay, and here's the problem somebody dumped on my desk. There is a way to bridge across there, use the math to get some goodness and drag that back into actual practice. Okay, so that's a skill. I think it's a hard skill to earn, but I want to at least admit up front, not just kind of pretend like we kind of did in the old days that, oh yeah, you'll figure it out. I want to address it a little bit more head on than traditionally. So I'll break down a search problem into a bunch of components and then talk about how we actually, what I can say, because I have to talk in generalities, right? What I could say about how we go from a problem that is not math to something that fits into an algorithm. And to give that teeth, we will try to use as many different contexts as I have time to talk about. So you can kind of see some generalities and some patterns hopefully coming up. That will the most useful thing I can give you, because whatever you see in the fleet will not be these little Blackboard problems that I'm going to put in front of you. That's for sure. So you need to get the general pattern, hopefully resides up here, that you can take forward in your career. And then we will start going through algorithms, and there are multiple search algorithms that are worth knowing about. So we'll talk about several of them. These are the kind of categories we'll use to analyze them, the computation they use, the memory they use, the quality of the solution, what we can say about that. We will first talk about blind methods. These are methods, blind always sounds bad, but it means that they don't require hints. So in a way, it's a good thing. The requirements for using the algorithm are as low as possible. So after we've done several of these, we'll talk about some extensions to those methods as listed here. That'll make more sense when we come to it, so I'll just leave that. And then we'll talk about informed methods, which can generally give better performance, but they do require some extra information, which isn't always trivial to give them. It takes some thought to provide that. Okay, let's move. Right, first thing is, search is a common term from English. So if you're not used to how CS people talk about search, you should not be thinking about searching for a name in a list, but that's a fine CS problem, but it's not the problem we're going to address in this unit. Or like finding a pilot in a big ocean, right? Those are valid things you can call search, but that's not what we're doing. Okay, so what we want to think of instead is searching for a solution to problems like path finding, being the big one. We'll talk about that more today. Or take another one. Let's say someone gave you a list of missions that needed to be flown, or we're planning an operation. We're ready to go, but here's the missions that need to go in the first week. They all take varying amounts of time. They all need to be done maybe by certain deadlines. They have very relative values maybe associated with them. Maybe some are kind of nice to fly, nice missions to fly if you have resources, but other ones are absolutely necessary. And on the other hand, you might also have the roster of pilots that's available to go, a roster of aircraft that are fit to fly at this point in time. You know what pilots have, what qualifications, can fly what aircraft, right? You putting that all together into a mission schedule is not a trivial thing, right? And that is a way does it seem fair to you to call that search? I'm searching for a solution to this problem, right? That's the kind of search that we're talking about here. Okay. All right, so here is the bottom line up front. This is like the main algorithm we're going to study. It'll all be variations of what's on this slide, all through the first unit till we say, okay, here we'll draw a line and let's talk about games. Talk about where you have an opponent. Okay, so here it is. So first thing, fine print. The algorithms rely on a processing list of partially completed solutions. What's a processing list? It's a list. You all know what a list is. You've seen that, as we call it a processing list, because what is the list actually holding? Partially completed solutions that are in process. Okay, so that's the idea. So that's in the background. Now let's just talk through the algorithm. It's just plain English here. Okay, select and remove the first partial solution from the list. Check if it's a complete solution. If it is complete, you're done. That is the one exit point for the algorithm. Okay, if not, then there are usually multiple ways to improve the partial solution. Try all of them. Okay? If any of those improved solutions, you notice that they have gone in a circle, okay? That's useless. We don't need solutions that go in a circle. Omit those, okay? But the rest of them go back on the processing list. Now, where they go on the processing list is what distinguishes these algorithms. That's it. Like the algorithms are all the same, except for this little detail, but this little detail turns out to be pretty important. Okay? All right, and then you loop back. Are we good? All right, just to be sure, let's talk about some fine print. When I say improve the partial solution, what does that mean? Okay? It does differ depending on the application, okay? But typically, when you're searching for a plan, a movement plan, or building out a schedule by assigning a pilot to a plane to fly a mission, okay, it means adding a little bit more to the plan than what you had already in that plan. Okay? Gone in a circle. Well, that's when your partial solution has made no progress compared to where it was at an earlier point. So for path planning, that literally means that you now look around and you say, yeah, I've seen that tree before. We've been here before. Yeah, that's not good. That's not a good path. Okay? For solving a puzzle, it might be that, you realize that the puzzle is now in the exact same configuration that it was 10 moves ago. That is not a good path to a solution, right? Okay. Clearly, you can omit that whole loop was wasted time. So that's not what we want. We want a better solution than that. Okay, and then, yeah, again, when I say add to the list, as I say, that's where the details are. Let's just, where are obvious places you can put these newly modified partial solutions on the list? Well, you can add them to the back of the list. You could add them to the front of the list, or anything else, okay? Or anything else. And there are more things that are important to know about. Okay? All right, so let's take as a whiteboard example to get started. What's actually a main example for us in simulation. So take planning on a road network. So I trust you've all seen this kind of a diagram. So these are points of interest, or maybe they're cities, lined between 2 points of interest means there exists a road. And it's not a straight line, like the right, this is an abstraction. It's not a straight line. And then they'll often put a number here, that's this little blur here that tells you like the actual mileage. So a lot of times in these diagrams, there'll be distortion where you got this little edge and then you look, oh, that's a big number. That's maybe it's a windy path that goes over a mountain or something weird is going on. Okay, that's what I'm talking about. So if we have a road network like this and we have a unit in the city and the user says, you will go here, right? What's a good path? That's what I'm talking about trying to solve here. Okay. Yeah, now we don't always use an abstracted graph like this. This is in mathematics what we call a graph, just balls, lines between them. That's a graph. Okay. More typically, we're on a square grid or maybe a hexagonal grid for some models. But a square grid or a hexagonal grid is a special case of this. What else do I want to say here? Oh, that's it. Stop me if I need to be stopped. Okay. All right. So we're going to do a little in-class exercise here. We'll just kind of go through that English algorithm to try to get some intuition about it. So path planning assumes a known start and desired end of a path. Yeah. It's not, we're starting from here. Where should we go? Path planner tell us that's a different problem. It's a fair problem. In some circumstances, that's not the problem we're solving right now. We know we need to get to this point B. We're going to draw the starting city as a white circle. We're going to draw the goal city as a black circle. Okay, and the roads that are actually used in our plan will be drawn as a thicker line as compared to unused roads. Let's show you an illustration in a second. So getting you ready. Okay. The starting solution is going to be a starting city and no roads, right? So it's kind of like a degenerate, what we call from a mathematical point of view, a degenerate solution, right? A path that actually, where there actually is no path. Yeah. Be generous and let me call that a solution. So it's a worthless solution, but we'll call it a solution. Okay. That's our starting solution. Now, when we improve the partial solution for path planning, this particular way we're going to improve it is we're going to look at the end of our current path, which is the heavy line, and we're going to add one additional road segment. Okay? And we'll consider all possibilities. Gone in a circle, just like what it sounds like. If we've actually looped around, then that's bad. That's gone in a circle. And adding to the list, what we're going to do just for now is to add new plans to the beginning of the list, right? And as we go through the algorithms, we will call this type of search depth first search for reasons that will become obvious. Okay? And ties are usually broken arbitrarily. So, if I have ties, I'll just break them arbitrarily. That's normal. Okay, so here we go. This is the algorithm that we talked through already. This is our processing list with our one solution on it, which is no path at all. We know we're here. We know we want to get here, and we've made no progress yet. So let's just step through the algorithm, okay? Select and remove the first partial solution from the list. Okay, there it is. There's the arrow is. We're pulling it out. Great. Check if it's a complete solution. Well, there's no path at all. So yeah, it's not a complete solution going from the white city to the black. There are multiple, try all ways to improve that solution. Okay, well, I could go to this city. I can go to the northwest. I can go to the northeast. I can go to the southeast. That's all the options. Okay. Check if any have gone in a circle. No, not yet. Too early for that. Okay, and then we add them to the list. Again, we add them to the beginning of the list, but the list was empty because we yanked off the only solution that was there. So adding to the front of the list is the same as adding to the back of the list in that case. Okay, so we just add them to the list. Again, I'm breaking the ties arbitrarily. In some contexts, it makes sense to have like a tie break rule. So you will know that children will go on in a particular order. That's not unheard of, but it's not totally normal either. So let's do it the easy way. It's arbitrary. There it is, arbitrary order. Good so far? Okay, that's one pass through the algorithm. Now you just keep going. Now we're going to yank off the first solution there. We check, what's going on here? What did I do? We check if it's a complete solution. Okay, we do have some progress. Okay, so better than before, but it does not end at the goal city. Therefore, it is not a complete solution. Okay, we continue to step 3. What are all the ways we could improve it? Okay, so from this city, we could go to this city. That would be, oh wait, where am I? Oh yeah, well, there it is. Oh, we can go to this city, we can go to that city, or we could double back, right? You look at all possibilities. Okay, now the next step is where we go and we check, did we get circular? This seems stupid, right? It's just like, well, of course it's circular. You just went right back where you were. Yeah, okay, but it's not always certain, right? I mean, think about a complicated puzzle where the state is actually complicated. Think about you're actually scheduling a bunch of pilots for a mission, and you're adding missions in, and you realize, oh, I went down a blind alley. This is not going to do it. You start yanking some out. Right, to realize that you're actually in the same situation that you were half an hour ago when you're working on that thing, that is not trivial. Okay, all right. So it isn't always like this. So that hopefully will help you realize why that's a separate step to check for that circularity. All right. So, all right, this is circular. So we throw that one out. All the other ones go on the list, and they go in front of the ones that were already there. Right, because that's what we agreed. That's what we agreed to. Okay. All right, let's keep going. All right, select and remove the first partial. All right, there we go. Does it end at the goal city? No, it doesn't. So we're not done. Let's think of all ways we could extend that partial solution. Okay, we could double back. We can go to this city, or we can go to the goal city. Okay. Now, it's irresistible to people who are just starting to look at this, who don't realize the pains that you're going to encounter when you actually have to think rigorously about these algorithms to say, there it is, it's the solution, stop. Why aren't you stopping the algorithm? No, we do this systematically. This is not where we check that we've got the solution. And in fact, you will get the wrong answer, according to some algorithms, if you check prematurely. Okay? Because part of their performance depends on you checking at the right time. Okay, so we will resist that temptation. So we try all of them. We go and we look for circularity. Okay, you're out. Okay, these other solutions go on there. Okay, and again, it could have been that the best one is at the very front of the list, but it also could not be because tie-breaking is arbitrary. So let's assume it's like that. Go back to 1, pull this guy off, check if we're done. Nope, not done yet. Extend the solution. Now here you go. Here you go. You see what's going on here, right? Not all circularities are equally obvious to see. Here's a more complicated one. Here's yet another more complicated one. And here's the one we keep seeing. We just go back to the city. So they're all bad. Okay? When we do the circularity check, they're all bad, which is fine. That just means nothing additional goes on the list. We just continue. Okay? And the whatever solutions, there aren't any. Great. Go back to 1, pull the first one off, check it. Complete path. We're done. All right, good. All right, well, that's it. That's what we're going to be thinking about and variations on that for a couple hours here.
How much additional complexity would it have to get the optimized path instead of just any path?
Well, stay tuned. Stay tuned. This is part of the subject for sure, but it's going to take us a while. Please be patient for me for like at least a 2 or 3 hour budget to let me get to that point. And I will get them. We're going to start easier. All right. Now this slide is supposed to connect you back to those agent sketches that we just did, because I just want to, because I don't constantly bring those back up to kind of explain. Remember the ones that were goal or utility based, but particular goal based agents? Right? Not just the reflex agents, but the one where you gave a goal, right? And then they had to know what'll happen if I do this or do that, how the world will change, and then they check that against the goal. That is exactly the kind of mold that we're in. And in fact, for some agents, today in modeling and simulation, that's the whole job of the agent. It's the only thing it cares about is going from point A to point B, because that's the only AI that's in the model. Okay? And then we have other models, and more of the newer people are getting more and more aggressive in terms of the AI they're putting into these models, where that's just like a detail, but they want it, they still need it. So the same functionality becomes a little block. It's more like a system of systems, and this is like if you can still call it an agent if you want, but it's just like a sub agent inside the bigger agent, which is representing the whole OP4 brain. Okay, both are possible. Okay, note that, and again, remember at the end of the hour, we talked about all these ways in which environments could be easier or harder. Okay, I want this to be as easy as these algorithms need it to be, generally need it to be as easy as possible. Okay, which means they're limited. Yeah, that's make it a little disappointing, but and you'd be surprised. There's still plenty of room for applying these, even with the restrictions. So we want the environment to be accessible, which means what?
You can be
Yeah, you can see the whole state of the world. There's nothing hidden, okay? Deterministic, not random. Static, that means it doesn't change while you're trying to making your plan, the world doesn't change. And discrete, no floating point numbers needed for these. It's a list of cities at the discrete set. Okay, now we will talk about relaxing the accessibility / determinism requirement later as kind of a little bit of an aside, but in general, we're going to assume things are easy. That won't be the whole course, but it is right now. All right. Yeah, I think I already said this. Okay, just don't worry about these are called blind search techniques. That's what they've always been called. And it's they are blind in the sense that they have no idea how close they are to the goal. And they're always surprised when they say, "Oh, look, here it is! It's the goal! I'm there!" They had no idea they were one step away, and no way to know that. That's the sense in which they're blind. Okay, but as users, to make an algorithm informed means you need to provide it some hints, which means extra work for you. So for us, we can get away with blind search. No, great, let's do it if we can get away with it. All right. Okay, now I want to talk about problem formulation, otherwise known by the name of domain abstraction. Okay, what this is about what I talked about at the beginning of the hour. It's about going from a real world domain, a real world problem, to the abstractions needed in order to apply a search algorithm to it. Okay, so in particular, we're going to need to produce certain problem components, states, right? This is what the world is at this moment, a representation of that. A goal test, right? You saw the algorithm needs to know when it's actually at the goal, so we need a goal test, operators, and path cost. I'll talk about that in a minute. Okay. Now, properties, so good problem formulation. This is not cut and dry. There's not right and wrong. This is where you apply your creativity, and the two of us can do it, and yours might be better than mine. And the decisions you make, unfortunately, are meaningful. You know, in AI, the way we choose to represent certain facts tends to be meaningful. The people who understand the AI algorithm that's going to process those facts and can put it in a better form for the AI are often going to be the winners. So we can have two sets of facts, and we know as people that, yeah, they're written differently, but they mean the exact same thing. It's the exact same stuff, yet they will function very differently when the AI is exposed to them. Okay? All right. Now, so that's problem formulation. It is an art. I like this quote by Einstein here. Everything should be made as simple as possible, but not simpler. It's almost like a Yogi Berraism there, you know. So as simple as possible, but not simpler. Yeah, simplicity is your friend up to the point where you've now thrown away, as we say, you've thrown away the baby with the bathwater. Yeah. And now even after you solve it, oh, it's solved, and then you realize that doesn't actually help you at all in the real world. You've done nothing that's actually useful. Okay, then you made it too simple. But short of that, we love simplicity. What we need is for every solution that comes out of your formulation, when we get to the goal state and the search algorithm is done, we need that to correspond to at least one solution in the real world. If not, that's what I say. That's where you didn't contribute anything. Okay. Now, it is, however, typical that one solution in the formulation is okay and expected. It may correspond to multiple solutions in the real world. In other words, there may be all kinds of details. You know, it's like if I give you the solution and I give you the solution on the road network, that still doesn't tell you, you know, what speed you should be moving the truck at each point along the path. right? There's additional stuff that has to go into that. And if you say that's also part of the problem that I care about, that's okay. But now we're back to what I'm saying here. Yeah, any changes in velocity of the truck that are needed, to go around the corner safely or what have you. Okay, if that's important, okay, that would still need to be dealt with by the human driver, by another AI, by something else. Okay, but at least I've contributed something. I've contributed something. I've given you a valid path to get to the end. So that's the mentality here. And yeah, hopefully when you get the abstracted solutions coming out of your formulation, it needs to be easier than trying to generate detailed solutions directly. I mean, it kind of goes without saying. Otherwise, once again, you'll be feeling like, why did I do all this work? It wasn't actually helpful. All right. Now, yeah, the practical aspect here is that once you take a search problem and put it into this canonical form, you can just drop it into a generic search code written by anybody, okay, and have it solve the problem for you. Okay, right? And that's a huge deal. All right, so what are these components? I listed them on the slide, but now I'll talk through them to make sure we're communicating. Okay, so what do you need to define? You need to say what the states of your problem are. So what are states in general? They're hypothetical descriptions of the world, perhaps a partial solution to the problem. We just saw like a partial path along a road network. That would be an example of a state. You need to also specify what the initial state is. That's the state of the world now that we should be starting from. Okay, some little fine print there, but that can't be forgotten. Okay, you need to specify operators. So this is a term of art. They've always been called operators. What these actually are more average human language is just actions, the actions that the agent can take to change the state. Hopefully to make it better, but to change it at least. We need a goal test. So a goal test is a logical formula or a function that returns true only for states that represent the achievement of the goals. And that's how the algorithm will know. That's how it checks the box for that one line of the algorithm where it says, check, are you at a solution already? It will use the goal test. Okay, the last thing is a path cost. So this isn't always used. But the idea of a path cost is it's a function that assigns a single cost number to a sequence of operations, the ones that are part of your current plan. It could be a complete solution, but often it's just a partial solution. Okay, and the idea here is it is a cost. Since I say it's a cost, the semantics is that higher numbers are worse. We would like the lowest cost solution possible. Any questions about this? All right. Okay. So I didn't bring my 8 puzzle today. I have one up in my office. I always forget to bring it these days. So this is like a physical thing, right? Have you all seen this kind of a puzzle? These are little tiles that are locked into this frame, and you can like slide this 8 up or 4 over. The other ones are pretty much locked in place. You've seen these things, right? You can go online and you can have a digital version of it real easily. It's a great time waster. My parents loved these and give it to me when I had to shut up and do this thing. And, it was entertaining to an extent. So the 8 puzzle, my point is, it's a real world thing. I mean, it didn't come from math. This is like an actual puzzle, but you might have one and you might actually want to know, right? Again, like most things in a class, we're not going to solve a lot of real world problems in here. Right? We're going to do small things. So this is a small thing, but it's a real world problem. Let's go through the drill and let's try to take it seriously, and let's go through and try to formalize it in appropriate way, so we could connect it to a search algorithm and get a solution. Okay. All right. For states, right? What are we going to need to do for a state? Well, here's an example of a state. It's a special state. It's the start state. Here's another example of a state. That's again another special state. That's the goal state. We're going to need to specify a location for each tile, right? Initially, it'll be in some shuffled location, shuffled configuration, such as the start state there. And you notice this is anything but shuffled. The numbers are just kind of sequential around the outside. Okay. All right, what operators are we going to use? Now, you might think, like I think, well, I might think, if I was exposed to this for the first time, you think, well, you move the tiles. So an operator might look like move the 3 north or move the 3 up, right? The 3 tile up. And then you realize that, well, that leaves you with a whole lot of possibilities that are useless because almost none of those you can actually do in an actual state. You know, at any given time, at most, 4 tiles are going to be able to move. That's the absolute maximum. So it's actually, and this is an example where I tell you creativity matters. So somebody at some point, not me, realized that, no, dummy, don't talk about the tiles moving. Think that it's the blank that you're moving, right? Because the blank can always move, right? So move the blank left. Okay, you can't move right here, but it can move left and it can move down. It can always move somewhere. Okay, so that's the smart way. So the blank moves left, right, up, or down. That's our complete set of operators for this problem. Yeah, we're all good? All right. All right, goal test. The state matches the one shown at right. Okay, seems straightforward enough. Path cost. Okay, so for path cost, so now this depends on what the nature of the puzzle is, right? And typically when you're handed this kind of a puzzle, the game is to try to not just to solve it, but ideally you'd like to solve it quickly. That's more impressive, right? One way to code that into a path cost is just to say that, well, every operation costs you 1. So if I solve it, but I'm not real good, and it takes me 100 operations to do it, and you're able to solve it in 10, then your cost was 10, but mine is 100. So clearly my solution is worse. Okay. All right. So just at the English level, that's kind of a complete formulation. All right, now, if we were actually, it was in the next slide, I know what it's going to ask. So think about this. So let's think about this a little bit deeper, kind of at the code level, or maybe the pseudocode level. Like, how would you actually specify a location for each tile in code? Like, what would that look like? There's a particular state right there. Like, what kind of data are you going to want to use? Any ideas? Please. What's that?
A matrix.
A matrix? How big of a matrix? 3 by 3? Okay. All right, so you can have, so if it's Python, or maybe this will work in JavaScript too, I forget, right? We could have like a 3-element list, and we can have a list of 3-element lists. So there's the first one, here's the second one, here's the third one, and close. Okay, right? All right, and then we can go, then it's pretty obvious. Even I can do this part, right? I can do 5, I can do 4. What do I put here? 0. Okay, right? So this is a decision you have to make. How am I going to represent that? 0 seems legit, right? Okay, 6, 1, 8, 7, 3, 2. Nice representation. Is it the only representation? What else could you do?
Well, you just do a list.
Okay.
Or like each position of the list.
Okay, so each position of the list, how do we do that? So how would you fill out the list for the start state?
It would just be a list that we go 5, 4, 0, 6, 1, 8,
5, 4, 0, 6, 1, et cetera, et cetera, et cetera. Okay, I think we get it. Okay, all right. What else could you do?
Store it as a string.
What's that?
Store as a string would be the same principle.
String. So how would that work?
It would be the same thing as the list. It would just be
With the commas?
without the commas.
Without the commas. So 5, 4, 0, 6, 1, blah, blah, blah. I'll accept that. Okay. That works perfectly well for this problem, so fair enough. You know, if it was a 4 by 4 though, we'd end up with an issue, right? Because we end up with numbers that are going to be 2 digits. And now we need a way to just, no, maybe you put the commas into the string. Okay. Okay, is that we exhausted all the possibilities? What else could you do?
Each number has like its own property of like X and Y value or something.
Okay, okay, yeah, that's kind of what I was thinking of. If we could do like this, right? So this could be, we have a list of pairs where these are the coordinates, right? Where this is the 0, which is the blank. And the blank there would be, I don't know, you got to decide how your coordinates are going to go. This is computer science, so maybe we start with 0, 0, 1. So X is 0, 1, 2, Y is 0, X is 2, right? So 2, 0 for the location of the 0, right? What's the location of the 1?
1, 1.
1, 1. Yeah, that's the location of the 1. Okay, what's the location of the 2?
Counts. 2,
2, 2. Very coincidental there. All right. We all get it? Yeah, so there's no end to these things, right? So you got to think, and often it does make a difference. So it's worth some thought. I'm not sure if this is the case where it's going to make a huge difference, but it often does make a difference. So realize that. Okay, to write operators, how am I going to represent the operators? What am I going to be doing? Is that also going to be data? Or is it going to be code?
That's probably gonna be code, because when you do something blank, it's gonna move your numbers around.
Okay, so code like a function.
Yeah.
Okay, so like,
Move left.
what would my, go ahead, what would
Like move left.
move left, okay, right? So we can say, yeah, move left. Right, and then maybe the number of the thing you're moving, so this would be n, which is 0 through 9, right? There's a range for that, right? Bump up, right? Write some code that would change the state. Well, we probably better pass in the state too, maybe. Unless that was a global variable, we need to pass in the state. Okay, and then this will return a new state, but with that thing moved to the left, or maybe throw an error and say, no, the 5 cannot move to the left in either one of these things, right? Something like that. Okay, is this the only way to do it?
If you're only moving the blank, you probably don't even need to pass it and.
Oh, that's true. That's true. Good. That's quite right. That's bad on me. Yeah. Why do that? You're only going to move to 0. That's only going to be 0 every time you invoke it. Why would you be doing it? Okay. Fine. Well, how else can we organize this? If we do it this way, how many functions are we going to have? 4. Yeah, we need 4 functions.
You could write one function that just spits out 4 new states, which are the 4 possible states.
There you go. All right, just move, right? Give the state, and it will return between 2 and 4 possible successor states. Is that clear to everybody? This is not meant to be. I'm getting lazy now. We've written enough, but I don't want to confuse it. Okay. All right. Right if we needed to. All right. Goal test. How hard is it going to be to write a goal test? What did you do? What would that look like? It's going to be code, clearly, right?
Depending on whatever the format is, you're doing a comparison and how you have to do
Like
it.
loop through it.
Yeah.
We've got 2 dimensions the way we started. Loop through both dimensions. Check every location. At one point, if it's different, what do? Return. No, not the goal. Otherwise, we get to the end. We say, okay, got to the end is the goal. Okay. And path cost. So we just need to know the number of operations. I guess that's pretty easy to keep track of that. Okay. All right. Let's see what's coming next. I know when to stop. Okay, so we can look at this. So this is just terminology again, but it's a great concept. We don't typically produce these when the algorithm is running. This is just kind of a learning tool. So this is known as a state graph. And it's kind of what you expect. Each one of the nodes in this graph are states. And 2 states are connected if there is an operator that connects them directly. Right? So if I'm here and I move the blank down, right, follow that arrow, we end up with this state. If I'm in this state and I move the blank up, I get back to this state, and you can see, okay, that this how this works. And this is obviously just a little part of a very large graph. It is part of the problem. Even the smallest things we dream up for classroom use are still too large usually to actually put on a slide. I'm delighted when I actually have something small enough I can like show you the whole thing. That will happen this quarter, but not all that often. Okay, let's see what's coming up next. Okay, a solution. I think we can do this. So a solution, again, this is just terminology. It's something I'm defining. I don't think it would shock you. Okay, a solution is just going to be a sequence of operators that are guaranteed to connect the initial state to the goal state. Right? So it'd be like the city list, the way you should move to move from city A to city B, or the ways you should move the blank in order to solve the 8 puzzle. A goal state is it's just a state that passes the goal test. There's nothing mysterious about that. What'll be interesting, I'll leave it here. This is the key point. Sometimes only the details of the goal state itself are of interest. I'm going to show you, like scheduling as an example, you could think about on your own. Am I really saying the right thing? I mean, for the 8 puzzle that I just showed you, the look of the goal state, you have to know that before you start, right? That's not why you're solving the puzzle, to see what the goal state looks like. You have to know that. But for a schedule, you're solving it to see what is that final schedule. You have no idea what that final schedule is going to look like. Okay, that's the difference there. Both types of problems are common and of interest. Okay, and the claim here, I'll let you think about this. We'll discuss this first thing tomorrow. I claim that you can write a goal test without being able to specify the goal state in detail, or even if you don't know if there is a goal state, you can still write a goal test. Think about that. Think of that. Is that an obvious point for you, or is that I mean, I think at least the first time I thought about it, that seems a little bit paradoxical, at least. We'll talk about that first thing tomorrow. Okay? All right. Thank you all.